Thank you. My name is Olga Golovneva. I work at MetaAI Research in a team that focuses on reasoning, alignment, and memory. And today I'll be talking about collaborative and modular training. Thank you very much for inviting me. So I'll mix my talk with some introductory information, maybe for those of you who don't work in this specific field, and pinpoint to some problems that exist in these areas and our attempts to resolve them. So we'll start with a mixture of experts models that represent a form of ensemble learning, where each expert, that's represented by Ram in this picture, takes same input and produce some output. And then we mix them somehow together. In this way, mixture of experts were defined way before deep learning era, but we will talk about their specifics in large language modeling. Next, we'll move to multimodal models. Multimodal models are models that combine different modalities, which is just different type of inputs, such as text, audio, video, images. We will move toward, as we are moving toward more general intelligence and our large language models become really good, it's only natural for researchers to expand these models with more ways to understand and reason about world. And we cannot reason without world, without understanding different modalities. However, simply combining text and image, even these two modalities, into a single model is still a big challenge and requires significant computational resources. That's where combining multimodal and MOE can help us, since a mixture of experts are more efficient. They can reduce the burden on computer resources while preserving or even improving in accuracy. So why a mixture of experts became so popular? To simply put, they are more efficient than their dense siblings of the same size. Mixture of experts are cheap to compute at test time, and they're much more parallelizable on training time. For training, each expert can be stored on a separate machine and produce their output independently from other experts. Still, there is a bottleneck of collecting outputs from different experts where they need to be synchronized together. At inference, for each query, only a small subset of experts is usually activated. And this makes MOE in deep learning different from classical MOE, where we combine weighted outputs from all experts together. In deep learning, the output of each query can only involve several experts. Consequently, the key design choice in MOE becomes routing function. Given a batch of queries, how do you route these queries to the best experts you have? First work that was applied mixture of experts in deep learning dates back to 2013, where in their paper, authors proposed to train a gating network that maps each input on each layer to distribution over the experts. And this synchronization on each layer becomes a bottleneck from the training efficiency point of view. I kind of combined three general design solutions in MOE architectures in these three big groups: decoupled, loosely coupled, and tightly coupled. In decoupled architectures, we train experts independently and then somehow combine them. For example, we can average outputs to make next token prediction. We can optionally add classifier or router to select sub-experts for averaging, as it was done in branch train merge paper. Or we can simply average model weights, as it was done in Llama 3 herd of models. In loosely coupled models, expert weights are synchronized from time to time as an elastic averaging. But the most popular, or we can train models separately in parallel, but fine-tune them together. In tightly coupled approach, which is most popular approach, where we train models together with router from the start on. For example, one of the most popular model, Mixtral 8 experts with 7 billion parameters. It had 8 feedforward blocks in each layer with a router network that selects only 2 experts for each token. As a result, this model was able to outperform larger SOTA models available at the time of publishing, as evaluated across multiple benchmarks. Here I want to stop at one of the approaches to overcome high communication costs during training by loosely coupling models during training. This paper was published last year and was called Branch Train Mix. In these models, we took a seed model that was Llama 2, 7 billion at the time, and we trained several domain-specific experts on different subsets of data. These experts were trained independently and in parallel. Then we combined these models and fine-tune on small subsample of data mixed from different domains to learn router weights. How we do this? For each expert LLM, to get a final model, we average weights we average attention weights. The motivation behind this is the assumption that self-attention layers are less domain specialized than feed-forward layers. But we keep feed-forward layers, and we add a router function that we fine-tune during that we train during fine-tuning. We show that this approach requires less GPU days as compared to similar approaches, and results in higher average scores. As shown on the bottom left picture, when we evaluate on domain-specific subsets of data, our average models outperforms or performs similar to domain-specific fine-tuned experts. Branch train mix approach is cost efficient. It combines several aspects to make it this efficient. First, it relies on continuous training, so we don't pre-train model from scratch. We take this Llama to 7 billion, which is quite good to begin with already. So we need less data to train it further. Second, it allows for linear scaling with compute size. Normally, when we increase compute size, we increase inefficient batch size, and it's not really linear. While here, we just we can add number of experts per GPU machines. And finally, it's efficient in terms of inference because we keep only feed-forward layers in the final model and select top 2 experts at the inference using our router. Here, I want to briefly talk about one of the popular problems in MIE, dead expert problem. When we fine-tune on some data, we can sometimes see that some experts take over much more tokens than the others. And some experts can even die, meaning that the probabilities of token being routed to these experts is close to 0. So on the top left picture, we show the distribution per layer, the probability of tokens being routed to different experts, and there is like a hole in between there. There was a dead code expert, so the probability of routing to code expert was close to 0. Then this issue was overcome with adding load balancing. And after load balancing was added, the probability distribution became more uniform. As a result, in the final model, we can see that even though the probability distribution is more uniform, still our domain-specific experts fire on specific tasks. As an example, here on the top GSM-8K task, we colored each token depending on which expert it was routed to. And we saw that it's mostly like red and orangish, which means that it was routed mostly to math and general expert knowledge. Human eval, which is code task, was mostly routed to math and code task, and general task natural questions was mostly covered by the general knowledge domain expert. Next, we will move on to multimodal models. Multimodal large language models are the models that can receive, reason, and output multimodal information. The process of using different modalities so that a model can learn from them is called multimodal fusion. On a high level, multimodal architectures can be divided into two groups, early and late fusion, and there are like different in-between approaches there as well. Early fusion combines modalities at the input layer. It creates fused representation that is then passed through a single model. In the late fusion, models are trained separately for each modality, and then they combine their outputs or decisions at some later stage. Early fusion is simpler and more efficient as it avoids separate processing for each modality, but it has issues when we need to combine modalities that have unique characteristics that has to be processed during modality preprocessing, such as discreteness of the text or continuous nature of the images. Late fusion models are truly modular and thus fault-tolerant, as individual models can operate independently. In late fusion, each modality is processed independently with their own models, and the outputs from these models then combine in a later stage. There can also be some intermediate approaches. For example, when we process each modality separately into a latent representation, fuse them, and then process the fused representation. Early fusion models were most popular in the beginning of this multimodal models era, when language models and vision models individually become quite powerful. But now, as we progress, early fusion models become more popular. As an example, here are two models released by Meta, chameleon and transfusion model. Transfusion model was presented here on this conference a few days ago. Both models consist of a single transformer model that processes and produces text and image data. Important research questions for multimodal models is how to create representations for modalities with different characteristics. In both works, each text string is tokenized into a sequence of discrete tokens from a fixed vocabulary, which is a standard approach in language modeling, as we all know. But the trick is here how to combine these representations with images that are naturally continuous. In Chameleon, we used discretization approach. We used external pre-trained image tokenizer, which encoded a fixed size image into 1,024 tokens out of a fixed vocabulary of 8,000 tokens. In transfusion, on the contrary, each image is encoded as latent patches using a variational autoencoder, where each patch is represented as a continuous vector, thus preserving the continuous nature of the images. The patches are sequenced left to right and top to bottom to create a sequence of patch vectors from each image. For mixed model examples, authors surround each image sequence with special beginning of image and end of image tokens before inserting it to the next text sequence, while in Chameleon we use single break token. Thus, in Chameleon model, we arrived at standard language models token representation, which we can feed into standard transformer model. While in transfusion, authors arrived at a single sequence potentially containing both discrete elements, tokens from text, and continuous elements, vectors representing image patches. To convert this data into shared space of a single transformer model, authors used lightweight modality-specific components within shared parameters. These are familiar embedding matrices for text that convert each token into vector and each output vector into discrete distributions over tokens. For images, authors compress patch vectors into a single transformer vector using linear layer or UNet connectors. Another difference between text and images is that text is naturally sequential. We usually read in one direction, while images don't have directions. So transfusion combines casual attention of text sequences and bidirectional attention within the elements of each individual image. Finally, the Chameleon uses standard next token prediction laws because it operates on tokens, while transfusion is trained with two objectives: language modeling and diffusion. As a result of those improvements, transfusion model systematically outperforms its ancestor on multiple benchmarks while producing high-quality images as a result of the input text prompt. Here you can see also scaling laws for these models. As we increase the model size of training compute, the improvement in performance across multiple benchmarks stays consistent. Finally, we will talk about multimodal mixture of expert models. There are not many multimodal MOE models these days. Still some, we are in the early stages here. There are so many ways how you can combine multimodal mixture of expert architectures together, and we will look into some of them. One approach would be continuous training. When you take a strong baseline multimodal model and use it as an expert, and then combine these experts together, as in the CL-MOE model, where authors used Lava 7 billion model as a baseline, as a backbone for continuous training. Still, probably most popular approach is training from scratch. Like on this example, UniMOE area and multimodal contrastive flows with LIMO. All these papers propose to use early fusion approach for multimodality, and then they have layer-specific experts that combine through rotor. All these models share a common discretization approach, meaning that the images are converted into tokens, and the expert training is tightly coupled. Finally, in Llama-4 herd of models, some feed-forward layers are replaced with mixture of expert layers, and some are still dense. Llama-4 employs early fusion approach, meaning different modalities are combined in very beginning of the model's processing through discretization approach, meaning the text is tokenized into tokens as usual, and images are transformed into a sequence of visual tokens through encoder. These tokens are then concatenated in a long sequence of tokens to train mixture of experts. There are two sizes presented with 16 and 128 experts. Additional change is the introduction of share expert. It was actually used in some other models as well. That helps to facilitate better processing. As a result, the model was able to perform strongly on multiple benchmarks. To summarize, we talked about a mixture of expert training approaches that include decoupled and loosely coupled, tightly coupled architectures. Which one should be used? Performance would be one obvious metric, but also compute budget. Can you afford training from scratch? Or you have to start from something pre-trained? Do you have enough GPUs to train in synchronous manner? Or for the fixed GPU budget, do you better go after large expert, but train one after another, as in light decoupled approaches? Multimodal early fusion versus late fusion. Late fusion become more popular because they probably learn better, both modalities, when they do it from scratch. And combining collaborative and model and training is an open area research. We just barely scratched the surface here. Yeah, I think that's it. Thank you.
I have a question. So MOE training seems to be very efficient in training, both like in BTX or maybe even the Llama 4. However, it's also hard to use in to serve, or even to serve in a small laptop. Like many people could train their own, use in inference their own small Llama 3. No, Llama 4 is so big, so it's better, but it's also very hard to actually use. What would you say about this kind of a discrepancy between the modularity in training and the modularity in inference?
Actually, as far as I remember, Llama 4 can be served on single GPU. That's thanks to its mixture of expert approach, because it activates just small number of parameters. In Llama 4, fine-tuning without LoRa will be a problem, or without some special tricks, because then you would have to, because you'll have to fine-tune all 128 or 16 experts. But since it's activates just some subsample, inference is very efficient.
In BTM, so you can do multiple rounds of training independently and then merging back together. In BTX, it's a single round. Will you see something similar where you could run like one BTX that create an MOE with 4 experts, on the other side another BTX with 4 experts, and then you merge them again together, so multiple round, kind of like the command A from Cohere, where you do multiple round of merging and training.
Yes, that sounds possible. Still will be quite expensive to combine because you probably need a lot of experiments to figure out how to combine them together efficiently. What we saw in BTX experiments is probably scaling with more data, with more domain-specific expert would be a very good choice, because when we have domain-specific experts, what we showed is that combined model is very good at selecting correct expert. So once you have this data-specific, task-specific expert, then BTX approach will be very efficient.